So in the Lewis model, we represent the valence electrons as dots. And we're only looking at the valence electrons because these are the ones that are most important in bonding. They're on the outside, they're most loosely held. So those are the ones that are going to get lost. When we write a Lewis symbol for an atom, we show the valence electrons as dots around the element symbol. So let's write a Lewis symbol for oxygen. So the chemical symbol for oxygen is a capital O. That's pretty easy. And then we have to ask ourselves, how many valence electrons does oxygen have? What group is it in? It's in group 6. It has 6 valence electrons. So we're going to put 6 dots around this. Oops, that was too close. So what I did is I put 1 on each side, top, bottom, right, and left, and then I paired them up. This is a little bit like dice, right? So if you have dice, 6 is always in the same shape, right? Because then you don't actually have to count the dots. You can look at the pattern and see what you've got. So instead of doing oxygen with just a circle of electrons where you look at that and you're like, I'm not sure how many, we pair them if needed. So we've got 4 positions, right and left, top and bottom. That's oxygen. So we put the dots 2 per side, and that gives us a simple way to visualize the valence electrons. So if an atom has 8 valence electrons, it's called an octet. If you have 8 people singing together, it's called an octet, right? Atoms with 8 valence electrons are particularly stable. Which elements have 8 valence electrons? Noble gases. Do they make compounds? Not so much, because they're cool all by themselves, right? So, and of course, helium's an exception. So 2 people singing together is a duet, right? So helium has a duet of electrons, which is also good, but just for the little guys. So we have what we call the octet rule. Atoms will transfer or share electrons to achieve an octet of valence electrons. So you got 2 different, or actually 2 of the same atoms. They're going to get together and figure out, can we share or transfer valence electrons so we can both have an octet? And this is how the Lewis model predicts bonding. So let's look at ionic bonding. So if we draw a Lewis symbol for potassium, how many valence electrons does potassium have? 1, right? And chlorine has how many? 7, right? So there's 1, and there's going to be 2 on each of the other sides. You guys just have the giggles over there. It's okay. It's better than crying. Not that I've actually had people cry in my class, but my husband has. People take his exams and they leave in tears. Question? That's a good question. How do I know that chlorine has 7 valence electrons? Chlorine is in group 7A. So it's the group numbers at the top. On this periodic table, they're in Roman numerals. Or if you want to use the other ones, like 17, just knock the 1 off of it. 7 valence electrons. So we're going to look at these guys, and of course I personify these. And so potassium wants 8 valence electrons, and chlorine wants 8 valence electrons. And so for potassium to gain electrons, it would have to gain 7. That sounds like it's going to be pretty difficult, and it would be. We know that potassium will lose its 1 valence electron. And we can look at the electron configurations and see why that is good for it. So here's the electron configuration for a potassium atom. So here, 1 valence electron. This is the valence electron, right? The highest occupied principal energy level. If we take that guy off, now there's none there, so we probably wouldn't even write that. What's the highest level now? 3. how many electrons in that third level? 8, right? So potassium's pretty willing to lose this electron. When it does that, in the Lewis structure, it looks like it has no valence electrons. But we have to understand that we're just taking off that outer part layer, and underneath is this nice full layer. So potassium's willing to get rid of this. Chlorine's over here saying, can I have that electron, please? I just need one more, I'm so close, right? I just need 8. And potassium's like, sure, I can do that. So that electron from potassium gets transferred to the chlorine. Now we've got charges though, right? The potassium lost an electron, so it's got a positive 1 charge. The chlorine gained an electron, so it's got a negative 1 charge. You can kind of imagine how that negative sign could get lost in the dots, and so what we usually do is we put brackets around the Lewis structure and put the charge on the outside so they don't get mixed up. Any questions? Potassium ion and chloride ion then form ionic bonds because of opposite charges, oppositely charged ions. Okay, use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. Okay, so I'm not sure why, but I'm going to make nitrogen green. How many valence electrons does nitrogen have? 5. It's in group 5A, right? Maybe purple. Magnesium's going to be purple today. How many valence electrons does magnesium have? 2, right? 1, 2. Okay, so these guys are trying to get together, help each other out, so everybody gets 8. Everybody's happy if they've got 8. So nitrogen would like to gain electrons, right? So nitrogen is saying, hey, you've got those 2 electrons there, give them to me because I need to gain 3 electrons. And the magnesium's like, okay, because if I get rid of these 2, then I've got a full valence shell underneath, and that's what I'm going for. So those 2 electrons come over to the nitrogen. Now the magnesium has a 2+ charge, and the nitrogen has what charge? Gained 2 electrons, it's got 2-. Everybody good? No. Magnesium's happy, nitrogen happier than he was, but still not so good. What can we do? Well, is there ever just one magnesium atom sitting around? There's probably a whole bunch of them, right? So let's just bring in the neighbor. So here's another magnesium. This one also has 2 valence electrons. So the nitrogen begged 2 off of that magnesium. He's going to come over here. Can I have 1 of those? The magnesium said, I'll give you 2. No, I just want the 1. Okay. So 1 of them goes over here. Now we've got a plus charge on the magnesium. And what's the charge on the nitrogen? 3-, right? Is the nitrogen happy? Nitrogen's very happy. He's got his octet. He's good. This magnesium's happy. This one not so much. What do we do? Well, if there's 1 nitrogen atom, there's probably more nitrogen atoms. Bring in another nitrogen atom. You're like, this could go on all day. No, it won't really go on all day. We'll finish it. So that nitrogen atom is looking for electrons. This magnesium is looking to get rid of an electron. So you kind of see where this is going, right? So get rid of that one and give it to the nitrogen. Well, now the nitrogen has a -1 charge, and the magnesium has a 2+ charge. This magnesium is now happy. Is this nitrogen happy? No. We need to bring in another magnesium atom. Now we're going to be good because this nitrogen needs 2 electrons. That magnesium needs to get rid of 2 electrons. So they're going to help each other out. And now this this magnesium has a 2+ charge, and this nitrogen has a 3- charge. So we're supposed to be predicting the formula. Well, how many magnesium atoms did we need for us to come out even? We needed 3, right? So Mg3, and how many nitrogen atoms? 2. Mg3 and 2. This is why it happens that way. We learned how to just predict this in, I think it was chapter 3. But now we know why. Any questions? Yeah. No. It does not matter where you put the electrons. I put them the way I did just so they'd be closer to where I was going to bring electrons from. The only rule is no more than 2 on a side, and you can put them on the top, the bottom, the right, or the left. And generally you put them singly first and then pair them up. But exactly where you draw them doesn't matter. So the formation of ionic compounds is usually quite exothermic. When sodium reacts with chlorine, it gives off a lot of energy. It releases 411 kilojoules for every mole of sodium. Well, we could look at the ionization energy. The ionization energy for sodium is positive. So we have to pay sodium 496 kilojoules per mole for it to become an ion. The electron affinity for chlorine is negative 349 kilojoules, so that's releasing energy. But if you add those two together, that's telling us that transferring an electron from sodium to chlorine is actually going to absorb 147 kilojoules per mole, when we know from experiment that it releases 411. So something is missing. And what's missing is the lattice energy. So the lattice energy is the energy associated with the formation of a lattice, a crystalline lattice of alternating cations and anions, and technically from the gas phase. So when you've got those positive and negative ions and they come together and form a pattern, energy is released because the potential energy is lowered when they come together. So this reminds me of magnetics, the magnetic building toys, and you can just kind of bring them close together and they'll start to make something, right? They'll just kind of snap together because the magnets attract each other. That's a lowering of energy. And so that's what happens with these positive and negative ions. So the formation of ionic compounds, and this is important, the formation of ionic compounds is not exothermic because the metal wants to lose an electron and the nonmetal wants to gain an electron. It's nice to talk about it that way. It's exothermic because when the formed cation and anion come together, it releases a tremendous amount of energy. So that's where the exothermic nature of these reactions comes from. So here we have an illustration. We've got a whole bunch of sodium and chloride ions in the gas state, and when those come together, they go smash up together like that, release a tremendous amount of heat. The formation of the sodium ions is endothermic. You have to put energy in. The formation of the chloride ions is exothermic, but it's not more exothermic than the other is endothermic. It doesn't explain what's going on here. It's the coming together that releases the energy. That's the lattice energy. The easiest way to calculate what the lattice energy is to use a Born-Haber cycle. And this is based on Hess's law. Hess's law says that if you can write individual steps for a reaction, the change in enthalpy will be the same, regardless of how the reaction occurs. So we can do a hypothetical set of steps to show the formation of the ionic compound from its constituent elements. We can, and what we're going to do is we're going to choose steps for which we know the standard heat of formation. So we can add up all the standard heats of formation because we look those up in a table. And then we also have to know the overall change in enthalpy. That can be measured. One way to do it is like what we did in experiment 6B. We just used 2 styrofoam cups, and we measured delta H for the reaction between copper and the copper sulfate and the ammonia. So we need the overall change in enthalpy. And then the lattice energy is the difference between the heats of formation and the overall change in enthalpy. So this is a Born-Haber cycle. Now what's going on here? We're starting right here. So we're looking at the formation of sodium chloride from sodium and chlorine. And so this is formation, so we're looking at 1 sodium, half a chlorine molecule to form 1 sodium chloride formula unit. So that is the heat of formation. So we can measure that. We can look that up. But then what about the rest of this? So we're going to imagine that we're taking, here we have sodium solid and chlorine gas, and we're going to make the sodium solid into a gas. Now that can be done. So there's a heat that's involved in making that into a gas. And then we're going to take this molecule of chlorine and make it into an atom. And that's going to require us to put energy in. Then we're going to form ions. We're going to form an ion of sodium. That requires us to put more energy in. So we're looking at all the endothermic processes here, adding energy. Then making the chlorine into an ion. So that's going to release some energy. Now what we're trying to calculate is from the ions in their gas state to the solid ionic compound. That's the lattice energy. So that's the difference here. Well, we can't measure that directly, but we know all these other steps, right? If we were thinking about distances, if I know the distance between here and here, and I know the distance between here and there, then I can find, wait, that's wrong. And I know the distance up here. Because what I'm looking for is this distance. Right? If I know the whole thing and I know this part, then this part plus the thing I'm missing must equal that. Right? That's what we're doing here. It just looks a lot more complicated over there. We're looking at the individual steps of taking the normal reactants and making them into ions in the gas state. And we can look up all these individual steps. Any questions? Clear as mud, right? There are trends in lattice energies. So let's look at the alkali metal chlorides. So we've got lithium, sodium, potassium, and cesium chloride. The lattice energies have a trend here. Lithium chloride has the highest lattice energy, it releases the most energy, and cesium chloride releases the least. So why is that? Well, the chlorine is the same, but the metal cation is different, and so that must have something to do with it. So here we have illustrations of the ions and their sizes So lithium is the smallest and cesium is the largest. The chloride ions are all the same. Well, the distance between a lithium ion nucleus and a chloride ion nucleus is 241 picometers. It gets larger and larger as you go down because the cesium ion is a lot bigger, right? And yet, this is like somebody wearing one of those dinosaur suits or something. You can't get close to them, right? Because you got this big inflated suit on, right? And here, this one is just wearing a sweatshirt or something. I don't know where these things come from. So the lattice energy is going to depend on how close the ions can get to each other. And that is part of Coulomb's law again. Remember, Coulomb's law said the energy was proportional to the charges times each other divided by the distance between them, so the radius. So large radius, small energy. Small radius, large energy. Small radius, larger lattice energy. The charge also has an effect because Coulomb's law tells us that the energy is proportional to the charges. So if I have +2 and -2, or +1 and -1, I can expect a different amount of energy. So we could look at sodium fluoride and calcium oxide. These two compounds were chosen because they have similar distances between the nuclei. So sodium and fluoride, 231 picometers, calcium and oxide, 239 picometers. Very similar, and yet the difference here is big. Calcium oxide minus 3,414, sodium fluoride minus 910. It has to do with the magnitude of the charges. Here we've got +1, -1. Here we've got +2, -2. So just looking at Coulomb's law and other things being similar, we'd predict that this is 4 times larger, and it's pretty close. Questions? So the lattice energy, remember, negative lattice energy is exothermic, releasing a lot of energy. Lattice energies become less exothermic as the radius of the ions becomes larger because they just can't get very close to each other. Lattice energies become more exothermic with increasing magnitude of the charge. So these are fun problems. Arrange the following in order of increasing magnitude of lattice energy: lithium bromide, potassium iodide, and calcium oxide. These problems are tricky to make up because you have to choose the compounds very carefully. Because if you choose badly, then you can't predict them at all. So what do we have here? We've got lithium bromide, so that's Li plus and Br minus. And we've got potassium iodide, and we've got calcium oxide. So there's two things happening. We've got differences in charges, and we probably have differences in sizes. Well, these two have the same charges. This is larger charges, right? So if energy is proportional to Q1 times Q2, that would be 4, and this would be 1 and 1. So this one's going to have the largest lattice energy because it's got the largest charges. So again, we're doing that in order of increasing. So we're going to put the big one at the end. So calcium oxide's the big one, and then we got to pick the other two. You can really only compare two things at a time, right? So we got that one out of the way. That one was clearly the biggest, and then we've got to compare these two. Well, lithium and potassium. Here's lithium, here's potassium. Is lithium bigger or smaller than potassium? Lithium is smaller. So this one's smaller and this one's bigger. And if we compare bromine and iodine, iodine's bigger, right? Going down. And bromine is smaller. So this one has the two small ones together, and this one has the two bigger ones. So the distance between potassium ion and iodide ion must be larger than for lithium and bromide. These guys can get closer together. I'll write it down over here. The energy is proportional to 1 over R, the distance between them. Big distance, small energy. So this has the big distance, so smaller energy. This has the smaller distance, so the larger energy. So the lithium bromide is in the middle, and the potassium iodide is the lowest. Any questions? Let's look at how our bonding model for ionic bonds works compared to reality. So we know that sodium chloride solid is not going to conduct electricity. But if we put it in water, it does conduct electricity. So ionic solids generally do not conduct electricity. Well, in order for electricity to be conducted, something charged, a charged particle has to be able to move. Nothing's moving in here. When we put it in water, we separate the charged ions, and now they're able to move throughout the solution. What if we melt the sodium chloride? You can actually do that. Not at home necessarily, but it can be done. If we take this solid and we melt it, in a liquid, the ions are free to move relative to each other, and so molten sodium chloride does conduct electricity. The solid doesn't. Sodium chloride has a very high melting point. It takes a lot of energy to melt it. That tells us something about the strength of the bonds. These bonds are very strong, and they're non-directional, meaning the sodium ion is attracted to chloride ions all around it. And so there's a lot of strength in that bond. And so the bonding model explains the high melting point as well.